So we did two kinds of volumes yesterday in class. We did volumes with a cross-section that we could come up with a formula for, and they didn't necessarily have to be a constant cross-section, again, if we had a formula for the cross-section, like the two intersecting pipes. And then we had rotational volumes, which is what we'll look at here. And so I think this is the problem we ended class with the other day. We're going to take a chunk of parabola from 0 to 1, and we are going to rotate it around the y-axis. So whenever I'm doing these kinds of problems, just to try and keep my mind straight, I want to write down my function, I want to label my axes. We are going to be hopping around with different variables, sometimes x, sometimes y, sometimes others. So we want to label which axis is which. And anytime we're doing a rotation, we want to draw a little curly arrow around the axis we're spinning about. Okay, so that's important too, because it's going to change in every problem. It's always a good idea to attempt to then try and visualize the 3D object to the best of your ability, which is generally a challenge. And so when I rotate this, that point's going to make this circle right here. And then I'm going to have a parabolic base. So this isn't a circular bowl, it's a parabolic dish. So this is like dish TV. That's what these dishes are shaped like. Okay, they're not y equals x squared, but there's some other parabola 3Dized. So we want to generate this. One thing I know about this thing right here is at the top, the radius is 1, right? According to my graph. Otherwise, I need to come up with a radius in between as I rotate this sucker. Oops, that's not what I meant to do. Redo. The color, there we go. So at any particular point here, I need to know what that radius is as I revolve it. So that would be that right there. So how do I express this distance right there with the function I have? So first thing I note, is that a horizontal distance or a vertical distance? It's horizontal, and horizontal is which variable here, x or y? X. So that radius right here is x equals something. It is an x value because it's a horizontal distance. At the moment, my formula says y equals, so I need to rewrite it. So how do I rewrite that formula in terms of x? Square root. So what would I say specifically? X equals, it's really plus or minus, right? And sometimes the plus or minus matters, and we have to evaluate that at every case. All right, so let's see. The plus y is this black side here, and the minus would be that side over there of the parabola. I don't need that side. Okay, so I only need the plus here. So clarify, r in this case is the square root of y. That's my radius at any particular point. The method we're using here when we rotate like this, and we have a radius perpendicular to the axis of rotation, so please note that the radius is perpendicular to the axis of rotation. When I have a situation like that, this is what's called the disk method for doing volumes. Okay, so we're generating disks. So that right there means we're using the disk method. And so I need to describe what my circular disks look like. Okay, so up here, I have a little chunk of area that my radius is related to. That area gets rotated to give me this disk here. This width of the disk up there, that's on the y-axis, so it's dy. Okay. And then my radius I've already established right there. And the volume of a disk, anybody remember, is pi r squared, the base, times the height. So that means I'll have pi times the radius squared times the height. So that's a chunk, one of my disks. And then I want to integrate all of those disks as what variable, x or y here? As y goes from 0 to 1. Another good reason to put that y down there is so you don't accidentally grab a pair of x values that could be different. Like there was a problem on the exam that in one direction you were going from 0 to the square root of 2, and the other direction you were going from 0 to 2. And if you mixed those up, it didn't work out well, right? So we want to make a note to keep track of it. So the hardest part of all of these problems isn't the integral, it's getting to the integral, setting them up, all right? So now that we have an integral, find an antiderivative and calculate this volume for me up there. So let's finish that off. According to this work, the volume should be this sucker, 0 to 1 of pi y dy, right? Yep. And so if I state an antiderivative, do I need to put the integral symbol anymore? No, what do I put instead? Square brackets, yeah. So then once I have an antiderivative, I go square bracket, antiderivative is pi y squared over 2. And y is going from 0 to 1. And so I get pi over 2 minus 0, pi over 2 for the volume. And that would be units cubed. Yeah, that'd be a good thing to note because it is volume, units cubed or cubic units. Yep. All right, let's see. Do I have any other interesting ones to look at in my notes, or should we just pull from the homework? Recent post. Whoa, what are you doing? Stop it, stop it. Sorry about that, runaway mouse. Let's see, we did the box, we did the cylinder, we did the parabolic square type dish, we looked at the intersecting pipes, and all right, that's all I have there. Let's go play with the homework then. So we got the basics, it's now time to apply them. So is this 6-1, am I in the right spot? Yep, 6-1. Let's try question number 7's a nice number. Did you know 7 kind of worldwide is considered a nice, almost lucky number? Not in every culture, but it's weird. Other weird thing about whole numbers, odd numbers are perceived to be more masculine and even numbers more feminine. That's a weird one too. I don't get it. Anyway, let's see. Find the volume of the solid generated by revolving the region by the given line and curve about the x-axis. Okay, so we are given, blow that sucker up, the function 36, square root of 36 minus x squared. Does that look familiar? Can anyone recognize what that might be ahead of time? Yeah, that's a semicircle. Good, good, good. And then y equals 0. All right, so they say they bound a region and we're going to revolve it around the x-axis. So first step, sketch it out. New page. So I have y equals square root of 36 minus x squared, and I have y equals 0. And my belief there is that is a semicircle. And the radius is 6. And the center is 0, 0. And not a bad idea to whip out a graphing utility to double check that, plot a few points just to make sure. So I'm going to plot a few points. Let's see, if x is 0, then y is the square root of 36, which is 6, right? 1, 2, 3, 4, 5, 6. So I have a point up there. And if y is 0, then I get square root of 36 minus x squared equals 0. And sometimes we have to do some algebra. Squaring both sides, I get 36 minus x squared equals 0. Bringing the x squared over to the right, I get x squared equals 36. and taking the square root, x equals plus or minus 6. All right, so this is starting to feel like a circle with a few points on it, but a graph would be a good idea, and my scales don't match. Let's clean that up a little bit. I'll whip out GeoGebra for some help in a moment. GeoGebra doesn't help with the 3D aspect, though. It does? 1, 2, 3, 4, 5, 6. I didn't know that. 1, 2, 3. Well, I'll have to try that later. Maybe I'll even get brave and try it now. All right, so this is, I believe, that curve, and then y equals 0 is another name for the x-axis. So we've got this region right here. This is y. This is x. So again, good practice. When you make a graph, throw some numbers on there so we know what we're looking at. Identify the y, identify which axis is x. And then here, since it's a volume of revolution, we want to put a little curly arrow around the axis we're rotating about to keep it straight. At this point, we only know the disk method for revolutions. So that means my rectangle has to be perpendicular to the axis of rotation. There's a different method we'll look at tomorrow. So this is going to be, this height here is going to be my radius. Since, right, because I'm going to spin that around like that through the y-axis. So r here is vertical, so that means it's a y value, right? Okay, and we know what y is equal to here. So those are my radii here. What am I going to generate 3D here when I do this, when I revolve a semicircle like that? A sphere, yeah, it's going to be a sphere, yeah. Okay, so we're going to make a sphere out of this. And let's see, what else do I need to know? I have some symmetry in about the y-axis, so I could double an integral. Instead of going from -6 to 6 for x, I could go from 0 to 6 and double it. Okay, so that symmetry is good. A note on symmetry: if you're ever unsure if it's really symmetric, the test for, say, even symmetry is what we have here. If you plug in a -x and do some algebra on it, and it comes back saying, hey, that's the original function, that's the definition of even symmetry. If the negative sign pops out, it would be what's called odd symmetry. Okay, so just double check. If I replace x with -x, does that change anything here? And no, because of the square. Yeah, so this is definitely even symmetric. I do have the right to just take half of the domain here when I'm evaluating. So I think we have everything we need. Okay, as far as my disks over here that we're going to generate, their width is a dx, right? Always verify that. And we have the radius as a formula in terms of x. So I think we're ready to go. So the integral, I believe, for the volume, twice the integral from 0 to 6. And let's see, x is our variable of integration here. And it's always pi times the radius squared times the height of each disk, which is a little tiny height, and oops, which in this case should be not a dy, but a dx. So I think that's the volume formula here, using the disk method. All right, clean that up and come up with the antiderivative and evaluate it. So let's see. Let's see, 36 times 6 is It's 216. Sound right? And that is also 6 cubed. Actually, it'd be easier just write it as 6 cubed. Oh well. Let's see. 216 minus 1/3 of 16 should be 2/3 of 216. So I think the answer is 2 pi times 2/3. Whoa, that's a 3. Interesting. Let's try that again. Of 216. This 3 doesn't go not into 216. So let's say if I double 216, that's 432. Double it again, that's what, 864? 864 pi over 3? Anyone else get that? Help me, I don't have a calculator here.
216 does divide by 3.
Really? Oh shit, it does, right? Because that's 6 cubed. Oh, that's nice. Okay. So let's see, 3 goes into 216, what, 72 times? Is that right? 3 goes into 21, 7. 3 goes into 6 twice. Yep. Okay. Double 72, we get 144. Double that, we get 288. Okay, 288 pi. How's that?
Yeah, that's what I got.
All right. Well, good thing we're checking. Just another note I was thinking about as I was playing with this. The 216 is really 6 cubed, right? In both of those places. So I could factor out a 6 cubed. If I do that, just a note, another way to write this answer would be, I've got that 2 pi out front. I'm going to get then a 1 minus 1/3 here, because I factored out 6 cubed, so that's going to leave a 2/3. So cleaning it up this way, I get what? 4/3 pi times 6 cubed. Does anybody remember the formula for the volume of a sphere? It's 4/3 pi r cubed, which we just basically proved. So if we redid this whole thing with an r up here instead of a 6, we would have generated the formula 4/3 pi r cubed. Cool, huh? We just proved with calculus the volume of a sphere. That's exciting. Wow. Gives me goosebumps. All right, let's do another one. I think 12 was cute. Let's see. I marked it earlier as a cute one. Oh, yes, this is a cute one. All right. Oh, and it's given us the answer. Let's do a similar question so we don't know the answer. There we go. Now we don't know the answer. All right, so here we have x equals a function of y. Now notice we have stuff in the denominator, variables, which means we're going to have asymptotes flying around. So we're going to have to be aware of those asymptotes. We'll deal with integration with respect to asymptotes later. And then we have these other 3 lines, 2 vertical and 2 horizontal lines. So we want to try and figure that out. To do that, I think we might want a graphing utility. Oh, I said we'd whip out GeoGebra. I didn't quite get to that. But let's get GeoGebra here to help us with this. Because GeoGebra can graph y as a function of x or x as a function of y, which is kind of exciting. Yeah, I got to look that up. Darren says GeoGebra has 3-dimensional settings, and I'm surprised I haven't gotten to that yet. All right. So before I jump into GeoGebra, what's that? Oh, you can point them out. Okay. All right. I got to look. All right. So GeoGebra. You found it on yours? Ooh. Wow, that is wicked cool. Okay, so let's go to the app. All right. Oh, 3D grapher. Whoa. Okay, so the problem with this is then figuring out how to type 3D functions. Yeah, so for example, like 2-dimensional is a circle, right? X squared plus y squared equals r squared. 3-dimensional, all you do is throw in a z squared, for example. So just for fun, if I had x squared plus y squared, ooh, look at that. Oh, it put it in the wrong spot. Eek, that's some crazy stuff. All right, plus y squared. Ooh, check that out. It's a parabolic dish. Nice. Can I do a plus z squared, or is it going to freak out on me? Equals 6 squared, 36. Yeah, look at that. Whoa, that's exciting. Well, it's technically not a function we can integrate unless we solved for z. So like if we rewrote it as z equals like plus or minus the square root. So what if we tried the SQRT of 36, oops, minus x squared. So solving for z minus y squared look like that. Okay, so yeah, so now it's, so if I turn off this one right here, we just get the upper sphere. And then what if I try to integrate that? But so the problem with integration in 3 dimensions is you generally have 2 dimensions to integrate through. So you end up what's called a double integral. You have to integrate in one direction with respect to x and then perpendicular with respect to y. So I would have to type an integral within an integral here to make that happen and set up the functions right. So this is like Calc 4. So I'm going to have to stop right there. Not that it isn't cool, but it's a slightly off track. So let's, that is wicked cool though, huh? So you know what I'll try to do is, remember that intersection of the 2 pipes the other day? I'll come up with a 3D rendering of that we could play with in GeoGebra. Because I think you can grab this and rotate it. Yeah. So we could look around in that, intersection of the 2 pipes later. All right, I'll work on that. Something to do in my free time, which I have so much of these days. Just kidding. Not anymore. Okay. Maybe if it snows, yeah. All right. So I'm going to graph x equals, what was the one we got? 4 over the square root of y plus 1? Okay, so there's a graph of it there. I just want to analyze that a little bit on paper, but that's what it's going to look like. We were also asked to look at the lines x equals 0, which is the y-axis, y equals 0, which is the x-axis, and what was the other one? Y equals 1? Y equals 3. Okay, thank you. Where'd GeoGebra go? So y equals 3. All right, so it's this region bounded by the axes and this curve and that line that we're going to revolve. I think it's at around the x-axis. Let's double check that. Nope, the y-axis. Okay. All right, so let's play around with this a little bit. How are we doing on time? We're doing fine. So just if I were to solve this for y, it's not a bad idea to do that here just to get an idea for it. Control T. One thing to note is I could view this side over here as x over 1, and I could just flip both sides. So 1 over x must be equal to 4 over the square root of y plus 1. Oh shit, I wrote it backwards. I forgot to flip the other side. Weird. I know, yeah, that was interesting. Total brain fart. Y plus 1 over 4. Okay. You can totally blame me for today, yeah. All right, and then get the 4 over to the other side. So I'm going to have 4 over x, and then square both sides. I get a y plus 1, and subtracting 1, I get y equals, let's call it 16 over x squared minus 1. And so just a couple of things to consider. The original version of the problem tells me that if I let y equal -1, I have a problem, right? So that should be a horizontal asymptote. And this tells me the same thing, because what happens here if I let x go to infinity? Yeah, this is gonna go to 0, and y is gonna go to -1. Yeah, so I definitely have a horizontal asymptote at y equals -1, and because of the x squared there, I have another problem. I get a vertical asymptote at x equals 0. So I also have a vertical asymptote at x equals 0. And it's a good thing they told us to stop at y equals 3, for example, because this function rises forever toward that vertical asymptote. Oops, where's GeoGebra? Right there. Yeah, so this is going to keep going up and up and up, and the curve is going to keep trying to get close to that axis. And it turns out in some cases, we can find areas that seem infinitely long, and sometimes it works out. It's very bizarre, but we'll take a look at that toward the end of the course. But it's this region right here I want to evaluate. All right, so I'm going to steal that. Nah, we'll just graph it by hand. All right, so graph of this. Always a good idea, even if you have it on your calculator, to do it by hand, because we got to figure out what our radii and disks look like. So we know we have the point x equals 4, y equals 0, and we can see if we plug in y equals 0 here, we get 4 over the square root of 1, which is 4. If we try to let x equal 0, we have a problem. That's not possible. Okay. And so some other points would be handy. For example, 1, 2, 3, we were asked to plug in essentially y equals 3, because we have that horizontal line there. So if I plug in 3 for y, 3 plus 1 is 4, square root of 4 is 2, 4 over 2 is 2. So it looks like I have the point 2, 3 on this graph. So I think that's enough. The graph looks something like that. For fun, if you wanted down here, you could make a note that there is a horizontal asymptote that this thing is heading toward from above. And we are rotating this area about, it was the y-axis, correct? Y, x, so I want to put a little curly arrow around there. We are in the disk method section, so that means our disks, our areas, our little rectangles have to be perpendicular to the axis. So then my disk, a disk might look like that right there. So that means I have a delta y to consider. And so I should be integrating from 0 to 3. Let's see, that is a horizontal rectangle, which represents my radius. So the radius must be x or y. Horizontal is x, right? So r is an x value, and I happen to know what x equals up there. So our radius happens to be 4 over the square root of y plus 1. Putting that all together, I want to integrate as y goes from 0 to 3, pi times the radius squared times the height of my rectangle, which in this case is a dy. And my radius is 4 over the square root of y plus 1. So now we need to clean that up, right? So this all involves, when I spin that, right, I'm going to generate these cylinders, these thin, micro thin cylinders. And the volume of a cylinder is always pi r squared h. So that's where this integration formula comes from for the disk method. Okay, so let's see. 4 squared is 16, so I can pull out a 16 pi. Square cancels the square root. So I think we've got, for a volume, 16 pi times the integral as y goes from 0 to 3 of 1 over y plus 1 dy. Somebody want to suggest an antiderivative for 1 over something? What is it? No, if there were a square in there, maybe it would be like an arc sign. But if it just natural log, yeah, 1 over x, 1 over y, that's just the natural log. A u substitution is sometimes not a bad thing to be safe. So just consider for a moment, if I let u equal y plus 1, what's du going to be equal to? 1 dx, don't forget that dx. Okay, so I could rewrite that, what's that? Oh shit, dy, right? We switched variables. Thank you. Dy. So with that in mind, ignoring the boundaries for a minute, I could say this is the same as integrating 1 over u with respect to u, and that is the natural log of the absolute value of u plus c. Okay. All right, so bringing that back into this then, substituting back, I got the 16 pi chilling out front. I have an antiderivative, which is going to be the natural log of the absolute value of y plus 1 from 0 to 3. So that's going to give me 16 pi, switch to curly brackets, the natural log of the absolute value of 4 minus the natural log of the absolute value of 1. I love the I love the natural log of 1. There we go. Why? It's 0. It says e to what power is 1? 0. So this guy here is 0. 4 is positive, so I don't need the absolute value anymore. So it looks like the answer is 16 times pi times the natural log of 4. And now we're going to try and draw it. It's not that bad. So looking back, or I'll just redraw the image, rough sketch of the image, it looks something like that right there. This is the area that we're revolving about that axis. So in the top, I have a circle of radius 2, right? And then straight down from the center puts me here. My radius jumps out to be what, 4? About there maybe? So I could draw, let's see if that's 4. Another 4 would be somewhere over here. So this is the bottom. And then it just slopes down like that. So we've got this curved, chopped off cone, kind of volcano looking. Make that a dotted line. That looks like a lampshade, yep. We just found the volume of a lampshade that, oops, let's see. So the dimensions of this, let's say, this is gonna be an interesting lampshade. Let's measure in, what would be a good measurement here? I guess it could be a little tiny lampshade if we measured in inches. It'd be 4 inches across the top. It would be, what, 8 inches across the bottom? And I think we had, what, 3 inches tall? And then somebody whip out a calculator. What is 16 times pi times the natural log of 4, roughly, to like 1 decimal place? So we then have a lampshade that has a volume of 69.7 cubic inches, for whatever that's worth. I guess we could turn it upside down and turn it into a fancy bowl that holds 69.7 cubic inches of soup. All right, let's try another one. Let's see, let's use what's called the washer method, and I have just enough time to set up a washer, but not time to finish it. Where's the homework? Laundry, is that what you said? That is a good point. I get tired when I have laundry piling up. Oh, I guess I should type the answer in. So you're saying I should just quit here and not have any more fun? 16 pi natural log of 4. Nice work. Oh, I wanted that to say fantastic. Oh, well. What's this one? Rotate around the X. Oh, this is a good one. Ooh. Yeah, let's go for it. We'll set it up. We won't finish it. No, it says use the washer method. So I just want to explain what the washer method is, and I can use this picture to explain it. So let me copy this in. We'll get it started. We'll finish it next class, or you could try and finish it for homework. Oh, what's the password if you don't finish it? I changed it from get it done. I think it's please get it done or get it done now. I made it a little longer to encourage you to not. I'll look in a minute. All right, let's see, screenshot, x-axis. Okay, so we'll take a look in a sec. Yeah. So yeah, the way the dates went in there is I told the computer I want all these homework assignments. I want to start here and end there, and it said, "Oh, would you like us to put them in there uniformly?" And I said, "Oh, sure. Let's see where they end up." And so the computer put the dates in there for me, saying if you're going to start on. Yeah, so they had all these weird dates. Yeah, so I need to go in and tweak them. I didn't finish doing that. Okay, so if I revolve this right here, just consider like this little rectangle right up there. When I spin that, what I'm going to get is a disk with a hole in the middle, right? Because I'm only taking this little chunk around that axis right there. So this line right there is going to give me that outside there. And this inner line is going to give me a cutout center. So this is a hole in the middle. That's why this is called a washer. And there's a super easy way to deal with washers. Bottom line, a washer is like a disk with another disk cut out of the middle. Agreed? So what you can consider is you have an outer radius, call that capital R, and you have an inner radius, call that little r. And the big washer would have had a formula of pi big R squared h, where h is that little thickness of the washer there. And then all we want to do is remove the inner washer, the inner disk. So you just subtract pi little r squared h. So generating washers is really no more difficult than generating disks. The only challenge is sometimes you end up with two parts to your integral. So if we were to integrate through that, right, we have just two more pieces in there instead of one piece to deal with. Not necessarily a big deal. We just need to say, okay, what is big R here and what is little r? Okay, so big R is the distance from the axis to the furthest thing away from that axis. What is furthest away from the axis here? 5, yeah. So big R is just 5. That's not bad. And little r is always the closest thing to the axis. So little r here has got to be the distance from here to the closest thing, which looks like 5 cosine of x square root. Yeah, so little r would be 5 square root of cosine of x. And here they're saying only integrate from negative pi over 4 to pi over 4. So putting that all together, I think I have the integral. Oh, let's see here, go back. Is this with respect to x or with respect to y? X, it's x because we're revolving around the x axis, and that's always your variable of integration with disks, because your little things here are always perpendicular to the axis of rotation, which means that little chunk there has to be a little chunk of the x-axis. So this h here is really a dx. So we're integrating with respect to x, which is nice because they gave me a function of x, so I don't have to manipulate it. So I would have the integral as x goes from negative pi over 4 to pi over 4, and put your parentheses. So we have our big R, which was what, 5? So I'll have 5 pi times 5 squared minus pi times little r, and little r was 5 times the square root of cosine, parentheses, 5 square root of cosine of x squared, close the integrand, and then dx. So the hardest part is the setup, but we just set up the washers for this one. So I'll review this one next class if you have any trouble in the homework tonight. Let's see what I set for the due date and the password before you guys run off. How do I get out of here? Save. And okay. Does it give me a date? It says it is due tonight. Okay. So I could either move the due date or give you the password. What do you want? Both? Okay. Fair enough. It's a snowy day. It's a good day to do both. All right. Settings per class. Go. And okay, the new password for this chapter is please get it done if you don't get your homework done in time. And then we are going to set it for tomorrow night. Please do some tonight, though, especially if you didn't do any last night. Okay, good. Yeah, because tomorrow we're going to switch to a new method. Instead of the disk method, we're going to try what's called the shell method, which is like making volumes with successive layers of paint. Just kind of wild. Like paper mache instead of clay on a wheel. So it's going to be very exciting. What's that? Will we do surface areas? It's kind of like, yeah, surface area on top of surface area on top of surface area until you get a volume. Yeah, it's pretty cool. So please do some 6-1 homework. I'll catch y'all later. Oh, good, you can do more.